Hey, welcome to my talk. It's going to be about Spring Boot and Project Leyden. Thanks for taking the time. My name is Moritz Halbritter. I'm working in the Spring Boot engineering team, mostly on the Spring engineering team, mostly on Spring Boot, but also on Started Spring.io, so the website where you can create your boot projects. First, I'm going to motivate the problem. So why do we care about this whole runtime efficiency, startup, memory usage at all? So first, which is directly connected to money, it's just cheaper hosting. Usually when you deploy to a cloud, you pay for like CPUs, you pay for network ingress and egress, and you also pay for RAM usage. So if you can get down your RAM usage or your CPU consumption, it will get cheaper and you got like more money to spend on useless HR meetings. The other thing is it's good for our planet, and I think we should do things which are good for our planet because we got only one. If we use less electricity, use less resources, we got more out of the planet, which is nice. And then of course there are optimized containers, so this is more for people who like metrics. They just start faster, they use like less RAM, less memory, you can run more of them, which is like they are just better, and from a purely ideal perspective, your container is as optimized as it gets. And I mean, we are like most of us are software engineers, we just like to optimize stuff, right? So we are just doing it for the sake of the argument. So what we are going to do in this talk is we are going to take a look at the Spring Boot application, and we are looking at like 3 deployment options we have. We have CDS, which is like class data sharing. We have the new AOT cache, which is new in Java 24. And then we take a look at Project Leyden, which is the AOT cache plus profiling plus code compilation. AOT stands for, if you're wondering, for ahead of time. So we essentially take the idea, we shift all the stuff we can do at build time, some of it we shift at runtime, we shift to build time, and just do it ahead of time before running our application. So how is this going to work? If you're using CDS, or if you're using AOT cache or other stuff from Project Leyden, there's a training run involved. That means you start up your application, and the application will essentially record what it's going to do. For example, loading classes, run the profiler, and stuff like that. This is called the training run. This is done before you actually deploy that stuff in your production. The results from the training run are then saved into the cache. It's a cache file. I'm going to show that later. And this cache file you can then use in your deployment run to make your deployment run faster. Okay, so the training run happens first, it creates the cache goes into the deployment run is then just faster. So if we can like start up faster, we can, if we get it down, like the startup time down enough, we can even scale to 0, which means you got like, if you got no requests, no instances running, as soon as the first request comes in, we start the instance fast enough so that the user isn't like realizing it that there was no instance. It starts up behind the scenes, handles a request, and then if there are no more requests, just scales down again. If you use less memory, that means in your cluster you can just deploy more stuff on the same node. Like if one thingy like takes 2 gigabytes and you got 8 available, you can deploy 4 services. But if it only uses like 1 gigabyte, then you can deploy 8 services. So you can deploy more stuff in your existing clusters, or you can like shrink down your cluster and just pay less for it. And another great thing is, which we are going to see afterwards, with the whole profiling and with the whole code compilation stuff, the JVM takes some time to get hot. So what essentially happens is you run the JVM, and the JVM observes your code. What is happening here? When a request comes in, it takes a look at all the branches and stuff where your code data flow is flowing. The JVM is learning, and after some time it generates like code for it, like optimized machine code, not the Java bytecode which is interpreted, but just optimized machine code. And there are multiple layers of that stuff. So it usually takes some time to get your JVM to peak performance. The first requests are slow, and they're getting faster and faster and faster, but it takes some time. And with the whole Leyden stuff, you get like peak performance almost immediately, because the training run already trained the JVM on what to do and to create optimized code. And this you can then use at the deployment run to just get a JVM which is like instantly there, and it's like really fast. Okay, like promised, we are going to take a look at CDS first, right? What are the requirements for Spring Boot with CDS? CDS is a feature which is in Java like forever, but as you know, Spring Boot 3 has a baseline of Java 17, so you need at least Java 17, and then you need Spring Boot 3.3, at least. It also works with 3.4 and 3.5, and it will work with 4.0.2. So that are your requirements, and I guess everyone has that already, I hope, at least if you're running Spring Boot 3. We have to talk about two more concepts because you're going to see them in the demo. The first thing is there is a system property which is called spring.context.exit equals on refresh. So what does this thing do? What does this thing do? There is a start. This is our application where it starts. And usually the non-lazy singletons are created by the framework. And then the initializing bean after property set is invoked. And then usually your application would just go there, lifecycle start is invoked, their context refresh event is like published, and then your application is running. If you activate this command line here, the exit on refresh, your JVM is shut down at that point. The idea is that the JVM starts up to this point where all the beans have been created, all the classes have been loaded, and then we shut it down. And this is used for the training run because you do not want to run your training run until like the end or even stopping, not stopping because it's listening on port or stuff. So we just cut it down in the middle, essentially, stop it right there because we have everything we need, like all the classes loaded, we know which classes are loaded, and then we can store them in the cache. So this is the first thingy. It essentially just stops your Spring application at a certain point, and this then can be used for the training run. And the other thing is there is a concept called the self-extracting executable jar, and you will also see this command here, the Java jar mode tools jar app my app extract. So usually if you deploy your Spring Boot application, it is like a big jar. It's like an Uber jar which contains more jars in it, right? It turns out the JVM does not like this concept very much, that there are jars in jars, at least not for the CDS and AOT cache stuff, because to get this magic working, Spring Boot has its own custom class loader, which knows how to deal with jars in jars, because Java just doesn't support that concept out of the box. But this custom class loader is not suitable for CDS, and you can't make it suitable for CDS because the Java team specified that CDS, right now at least, only works with their class loaders and not custom ones. So we had to get rid of this custom class loader. And how to get rid of it? You execute this command here, which works on like every Spring Boot application, and it just triggers a small piece of code which self-extracts the jar file into a folder, which is called like jar. It creates a lib folder, and it also creates a smaller jar, which is in this my app folder. So you now get like the big one, and a small one, and a lib folder. And in the lib folder, all the jars which are in this Uber jar are extracted there. So there is a Spring Web in there, and a Spring Framework, and maybe Jackson annotations. All your libraries you're pulled in are now in this thingy here, and they're just lying there as a list of jars. So no more jars in jars, they are now a flat list in this directory. And this thingy here essentially only contains your classes, like your code, and it also contains a manifest file, the Java jar manifest, which points it to those libraries. And this you can now execute like you would this file here with Java -jar, and then take the smaller one, right? In this folder, you have to execute this one. And this gets rid of the class loader, because now we don't have jars stuffed inside other jars. We just have them lying around on disk, and we can just execute it. So the custom class loader is gone, and CDS starts working. So those are the two things you need to remember for the demo. Stop it at a specific point in time. Extract the stuff beforehand. So I think this is the demo, but I'm going to show it to you in a real player because I can make it bigger. So The first thing is we're going to use Java 21 here, but you could also use Java 17, it doesn't matter. Then we're just going to build our application, and this is a Spring Pet Clinic application, the thing we mainly use for benchmarking. And we're going to run it once, so that we see how fast it starts up without any optimization. So this is the big fat jar with jars stuffed inside jars, and we're going to take a look at how long it does take to start. Okay, it starts up in about 3 seconds. We're going to kill that. Now we're going to extract it. So you now have a directory which is called optimized app. And let's see what's in there. There is now a smaller one. This is the small jar I was talking about, and there is this lib folder. And let's take a look at the lib folder. There's a lot of stuff in it. So all the jars which were in the other jar and the big jar are now in there. This enables CDS. Archive classes at exit, and then this is the cache file. It starts up, and because we supplied this context refresh on exit thingy, it now has stopped automatically, and what it has created is the CDS cache file. It's this one, the JSA file. It's 97 megabytes, and there are preloaded classes in there. And we can now use that file to just start it up. You point it to the CDS archive file, and then it starts up faster. And now it only takes like 1.5 seconds. Right? That's the magic of CDS. The thing you saw before, like all the running to a specific point, like the Spring refresh on exit thingy, that was the training run, and we got our cached file, which is the JSA file, which later around on the disk, and then we use that JSA file for our deployment run. You can copy that file around, but you have to take some precautions, but I'm going to talk about that later. Okay, so those are other benchmark numbers because we executed that on a powerful Mac machine, and those are numbers from a smaller size cloud machine, which is like more related to production. So when we just execute the fat jar, we got like 5.74 seconds. If we unpack it, just unpack it, like with the jar mode tools extract thingy, you're down to 4.7 seconds. That's essentially the overhead of the custom class loader, okay? You can use that here, this trick, completely without CDS. It's completely decoupled. It's just a prerequisite for this. And then we enable CDS, and now we got a startup factor of 1.9x. We're down to like 3 seconds when it starts. There is another optimization I'm going to talk about a bit later, which is called Spring AOT. This is a feature of the Spring framework, which essentially generates code to reconstruct your application context, and this is a small optimization, and it gives you like a little bit more, like 400 milliseconds. You win with that, and you're down to 2.2 seconds. Let's take a look at the memory consumption. This is the big jar, 392 megabytes. So this is measured from the outside. This is not your heap size. This is the process, the complete process, the process from outside. Essentially, if you're talking in Linux terms, it's the RSS. If you unpack it, it gets a bit smaller. If you use CDS, you're down to 317 megabytes, and if you enable the AOT optimizations, you're down a bit more. So you essentially save like 19.1% of RAM if you use that one. So what are the requirements to get like CDS working? For the training run and for the deployment run, you have to use the same JVM. It has to be exactly the same JVM, same patch level, same architecture. Like if you create your training run on a Mac machine and you're trying to use the cache file on your Linux production server, this is not going to work. The cache will just be ignored, right? And then you see like okay, it's not starting up faster. What was Moritz talking about? Like you have to use the same JVM. The class path, which is defined in the manifest, it has to be as a list of jars. No jars nested inside other jars. That's why we did all this stuff. You can specify directories in there. No stars anywhere, no nested jars. And your deployment class path must be a superset of the training one, which is complicated saying of you can append to the class path at the end, but you cannot otherwise change this class path anymore because then your cache will be invalidated. If you append to the class path the classes which are, or the jars which are at the end of the class path, They will just not get cached, but they will not destroy the cache in any time. They will not invalidate the cache. If you copy this cache file around, like the application.jsa file we've seen, you have to make sure that the timestamp of the jars, they must be preserved, right? This one is a pitfall if you do like Docker copy and stuff, because Docker copy usually changes the timestamps, and the cache knows which are the original timestamps to detect changes on the jar files. And so if you change the timestamps of your jar files, the cache is broken and it starts up slowly. So take care of copy it with the original timestamps. And then there is a problem with the training run. So you have to think about where do I do the training run? It should be as production as possible because you want to load the same classes in your production. And you may have like used databases, and when your application is started up, it may try to connect to a database. We are aware of that problem. If you scan this QR code or go to this very long URL here, we essentially have like smoke tests, and there are little documentation snippets which you can use to prevent database interaction while doing a training run. I'm going to share the slides. There is the QR code and the clickable link, so all good. Like DataJBA, JDBC, whatever, Mongo, Redis, everything covered. Those are two things to look out. For example, if you're using JPA, you have to specify the dialect up front, because otherwise on startup, Hibernate tries to connect to the database and ask it what are you for database, but you can essentially force it on this. So there are stuff like this, little snippets you just copy in and use them for your training run. Okay, as you may know, we have support for the Paketo build packs, for the cloud native build packs. It's usually Maven Spring Boot build image or Gradle Boot build image, and what this does is it creates an optimized container. And the cool thing is there is CDS support in the build packs. That means you can do the CDS training run when using build packs, and this stuff takes care of building the container image, and it also makes sure that the JVM used for building the thingy, for executing the training run and for executing in later in production is the same JVM. It also takes care of timestamps of files and stuff like that, so this just works. We're going to watch another video. Should be that one. Okay, so we're going to build the image with Maven. This creates a Docker image. Right, so it downloads a lot of stuff, and it creates an optimized container image for you. Okay, now we have that image in our local machine, and we can just Docker run it, just to see the startup speed. It starts up in about 3 seconds. So no surprise here, like the other one we executed with java-jar. Now take a look at what do we have to do to enable CDS. It's just like this configuration. You put it in your Spring Boot thingy, it enables the JVM CDS enabled, and then it takes care of it. So we are going to use the snippet here and just build it again. And then CDS picks up this, and like the cloud native build packs pick up this environment variable, and now they know how to do the training run. During the training run in the background, that was the training run. It's storing the CDS. You see a lot of CDS stuff. It's storing it in the container image. And now we can run it again. This time using CDS. It starts up in 1.8 seconds. So with the setting of one environment variable, you get like this speed up, which is, I think, quite a cool feature. Okay, so we got like CDS stuff covered. Now we're going to talk about AOT cache. The cool thing about AOT cache is that it's essentially the successor of CDS, right? It builds on top of all the stuff you already know right now. We have like the trainings run covered, we have like cache files covered. AOT cache is essentially that, but just better. So there are now like two terminologies with AOT cache, which is a bit confusing because everyone starts naming his stuff AOT cache. Yeah, so we have the AOT cache, which is from the JVM, and we have the Spring AOT thingy, which is from the Spring team. So the AOT cache, when I'm talking about AOT cache, this is a JVM feature which has been delivered by Project Leyden. So Project Leyden is the idea to just make the JVM start faster, use less resources, and generally be more awesome. Project Leyden has already delivered stuff, and the first deliverable was like the AOT cache. This is right now in Java 24. And the idea is to just improve the efficiency. So when I'm talking about AOT cache, I'm talking about the JVM stuff. Spring AOT is a Spring framework feature, essentially, which has been built for the GraalVM native image support, but we can now also use it to speed up the process even more. It pre-computes like the whole bean stuff when you're building your application and then reuses that when you run your application. And there is a small demo if you like. You can also use profiles and stuff like that. So there is a small GitHub where you can essentially see that one. So this is the JEP which delivered ahead of time the AOT cache in the JVM. So you see here it's released as 24. It's not a preview anymore. You can just use it. The requirements are the same as CDS, Spring Boot 3.3, but now you need Java 24 or later, because like the AOT cache is only in Java 24. Okay, but if you're already in 17, maybe you should upgrade to Java 24, because as Jürgen said in the keynote, it's just all around and very awesome release. And we're going to take a look at another video. Let me find it. It's that one. Okay, so we're going to use Java 24, and you can do that right now. No preview features, no magic with custom JDKs, nothing. Okay, we built the application once. We're going to extract it, like the same as CDS. And then we're going to do a record, right? This records essentially the classes which are being loaded. And this stores them in an AOT conf file, which is referenced here. Okay? Run it. The application automatically stops because of the Spring refresh on exit thingy. Now we take a look at what has been created. The AOT conf file has been created, which is only like 2.6 megabytes big, because it only contains like classes. Now we create the cache. So in this case, in CDS, the cache has been created right after the box. Here, there is a small step with a config file in there. So there are 3 steps. This creates the cache archive. Let's take a look at that one. Here. This is the AOT cache, right? And now we can use that by just pointing it to the AOT cache. So remove the AOT configuration stuff, just point it to the cache, and it's going to be picked up automatically. And you see 1.37 seconds, right? So there are more steps involved, like 1 step more. And what you get is essentially, this was the baseline, this was with CDS, this is with AOT cache, like the thing which is new in 24, which is another improvement of 300 milliseconds, which is like 2.2x startup speed improvement. If you combine that stuff with Spring AOT, so the JVM feature plus the Spring Framework feature, you end up at startup speed of 2.2 seconds, which is an increase from here to 2.6x, only for a training run. You can do that right now if you are already on Java 24, which is, I think, just awesome. If we take a look at the memory, the big jar, we unpack it, we CDS it, 370 megabytes. If you use AOT cache, the memory will stay the same. Okay, so the memory requirements are essentially the same to CDS. If you enable it with AOT cache, you end up with 303 megabytes. So now we have learned that we how to take care of the AOT cache. So what we essentially do is we extract the jar, we do a training run, which creates this AOT config file, which is quite small, which you could then ship to another machine. And then you can create the AOT cache with a create command, and then you can use this cache in your production to get it faster. The same caveats apply like CDS. You can't fiddle with the class path. You can't like copy files around. You can't use the JVM. It's essentially the successor of CDS, but has the same prerequisites. Okay, so now we are going to show what's coming next via Project Leyden. So this stuff you see there's a demo in there. It uses a JDK, but this JDK has been custom built essentially. So what we did is we checked out the Leyden project source code, compiled the JVM ourselves. There are pre-built images, but they are quite old. But to get the latest and greatest, code checkout, custom JDK build essentially. It's not what I would recommend for your production systems, but I mean to get like performance numbers, you sometimes have to do stuff like that. So what's coming next? Ahead of time method profiling. That's the idea too. When you do your training run, the profiler of the JVM already runs and it sees which code parts are exercised, and we store this profiling information inside the cache. So the next time we start up, we already have like profile information which can guide our JIT compiler to create better code. And this has been like yesterday evening, so I had to update the slides again, targeted to Java 25. Okay? So this has not been released yet, and it's targeted, and maybe stuff can change, but there is a high possibility that this stuff will land in Java 25, which is great because that's the next LTS release. And then we can use it. And then there is also ahead of time command line ergonomics. So if you are like, you have to right now execute like 3 commands. Create the config file, create the cache, use the cache. This job is essentially make it easier to not fiddle around with the command line, but maybe just 2 commands like you see in CDS. It's also targeted to Java 25, and of course they did it like in the evening yesterday. So this is coming with Leyden. And this one is the most cool feature ever. Not only profiling, but also compiling the code, right? When you do your training run, the JIT compiler and the profiler working together to create highly optimized machine code. And usually, when you shut down the application, this machine code is just thrown away. But if you enable this feature, the created JIT code is then stored in the cache file and can be used the next time you start it up. So the JVM is like instantly warm because it already has compiled code, which is really cool feature. But as you see, it's only in drafts. You do not expect it in Java 25. I have no idea when this will drop, but if it drops, it will be just awesome. Okay, last video for today. This one here. This one is a bit more complicated. So we're going to use our custom built SDK, which we call Leyden. We're going to build it once. We're going to extract it. Yep, that's the extraction. We're going into the optimized app and we're going to start the application. But let me quickly pause the video at the right time. You can see we are recording stuff here. And what we are missing is this whole Spring context refresh on exit thingy. So this application will not stop when we start it. What will happen is the application starts up and it will listen to HTTP requests because nothing is going to end the process. And then we're going to use this tab here to run a benchmark against it. Because we need to get the JVM to learn what code paths are exercised when we really put pressure on the application, like if we put load on the application. So we have to somehow train it in your training run, like this time with real requests and not only like let it load classes. And that's why we don't shut this down. So record the file, start it up. We now switch the tab. and we run OHA against it, which is a load benchmarking tool. And what you can see here, let me pause it at the right moment. It's not hot. Yeah, okay, now it's hot. The first request here, or this one, is slower. No, this time, here. That's the first request. The next batch of requests, the next batch, and this bar here is how many requests per second the JVM handles. So you see the first requests, and those are slower than when the JVM is hot, right? This is the JVM at peak performance. Just let the benchmark finish. And you see we got like 62,000 requests handled in like 15 seconds, okay? Great. So now the JVM, which is still running in this tab here, has been exercised with load, so that means the JVM profiler has run, the JVM JIT compiler has been run, and it now has created optimized machine code, which is currently living in memory, okay? Stop the application. It's now an AOT-conf file, and all the learnings with the JVM has done are in this conf file, and let's create the cache. This creates the cache. And I was amazed to see this one here, like C++ stack traces or whatever this stuff is. Maybe that's the reason it's still in preview. So there are still optimizations going on, but what it has been created is a cache file, and this cache file, it contains profiling data, and it also contains like optimized code. Here, that's the cache file. There is optimized code in it. And now we are going to use this file to start up our application. And now it starts in sub-second millisecond, which is crazy. Like there is JPA and Hibernate and stuff in there, and it starts below 1 second, just with enabled AOT cache. So that's the stuff which is going to be delivered by Project Leyden, which is, I think, absolutely awesome. Let's run a benchmark against it. And what you see here is the first one is still a bit slow, but then after a second, it essentially reaches peak performance. So the JVM does not take 30 seconds to get hot. It's like hot until 1 second, maybe 2 seconds. We see detailed graphs afterwards. But this is because it already has profiled and already compiled all the stuff in the background. It's all contained in the cache. It's just being used, which is just great. And here you can see it handles the old one handled 62,000 requests. This one handles more because the JVM was hotter faster to handle more stuff. Okay. Let's take a look at the startup time. Baseline, 5.74 seconds. We unpack it, it gets faster. We use the AOT cache, it gets faster. We enable code compilation, and now you're down to 1.47 seconds, which is a speed up improvement of almost 4x. And then you enable the AOT cache, which is like 4.4x. Okay? So let me repeat that for you. 4.4x, which is like, no, I'm not going to do the same joke again, but you get the gist. This is just crazy. Like with one training run, okay, granted you have to do like some load on it, but if you got that setup covered, you essentially start up your application like 4 times faster, which you got like sub-second milliseconds with a sub-second startup time with Hibernate, which is like absolutely awesome. And here we compare the warm-up. And here you can see this is the baseline, and the baseline reaches peak performance in 32 seconds. If you enable AOT profiling and store it in the cache, you end up reaching peak performance at like 25 seconds, and if you enable AOT profiling and the code compilation, you have peak performance at like 8 seconds. This stuff you're seeing here is the overhead of the profiler and the JIT compiler. Your CPUs are busy profiling code and compiling code in the background. Here, your CPU, this here, your compiler is busy compiling code, and this here is like just use the cache. Ideally, those lines should match up, because right now it looks like that the baseline is a bit faster afterwards, but Leyden team is working on getting those here to match up. So you get the same performance when using cached compiled code as when you just use the JIT compiler. Okay, now I think your brain is already exploding, but let me explain this metrics. So you may have heard of native image, GraalVM native image, which is another absolute awesome technology. And Project Crack, which is like a checkpoint coordinated restore at checkpoint. The idea is essentially to take a memory dump and store that memory dump, and then when you run JVM, restore it to get it start up instantly, and the AOT cache. So when should you use what? What are the trade-offs? Because like, let's not pretend there are no trade-offs. There are always trade-offs somewhere. And here, this slide shows where the trade-offs are. So take a look at the startup. If you compile your application with GraalVM native image, you got like an instant startup. And instant is like 50 milliseconds, 100 milliseconds. Like it's crazy, crazy fast. Project JVM is the same. It just restores the memory dump, which is lying on disk, and your process is instantly there. JVM with AOT cache, as you've seen in my slides before, it's like 2 to 4 times faster. It depends on your application, how much stuff is your application doing, how you set up the training run and stuff like that, but usually you get 2x to 4x. Let's take a look at the warm-up. Native image is instantly warmed up because all the code compiling has been happen ahead of time when you build the native image. Everything is contained in there. There is no JIT compiler involved at all. With Project Crack, you essentially have the same with AOT cache. You need to do your training run right, and then the JVM for which you create the memory image is instantly hot, and then you can store it, restore it, and it's instantly hot when doing the training run correctly. And the same is with AOT cache. The reason why there is a fast with training run and here is instant with training run is just because the JVM team is still working to optimize this curve so that it's hot immediately. How to get the optimal peak throughput, so to handle X requests in a given amount of time. If you use a training run, another training run, with the Oracle GraalVM, which is the enterprise offering of Oracle, you can create a native image which is built on a special mode. You deploy it, you put load on it, and this thing spits out a file which contains essentially profiling information, which you can then feed back into the building of your native image, of your next native image, and then it's faster because it has just learned how to behave in your production system. So this thing here is, if you do the training run with Oracle GraalVM, it's very fast. It's comparable to those, but you have to do this training run. If you use the community edition, it's a bit not so fast as a highly optimized JIT compiled hot JVM. JVM with Project Crack, because it's a JVM, you get optimal peak throughput after some time, and the same you have seen it with JVM with AOT cache, you got optimal peak throughput. Take a look at the memory consumption. The GraalVM with native image, it uses less memory. The reason for that is because there is no JVM running. It's a smaller VM, which is called substrate VM. And the thing just uses less memory because you do not need profilers, you do not need JIT, and they do some other crazy magic to get the memory consumption reduced in GraalVM native image. With JVM with Project Crack, you got like no gain at all because you just take a usual JVM, make a memory dump, restore it, and memory hasn't changed at all. And with JVM with AOT cache, you saw it in the slides, it's a bit reduced, but yeah. Okay, let's take a look at the compilation. So if you ever build a GraalVM native image, you know that the native image compiler takes time and it eats a lot of memory while building the native image. So it's cool. It's heavy and slow, right? And they are improving, so the GraalVM team is hard at work at improving that stuff. It was worse before that, but it's still not at the Java C level of performance. Like, it takes some time. JVM with Project Crack and a JVM with AOT cache, there is no difference because you just do Java C compile and then the thing is there. Compatibility issues is essentially how easy it is to compile your existing application to a native image. And if you ever tried it, it works sometimes out of the box if you do not use like too many third-party libraries, but if you're using an incompatible version of a third-party library, stuff starts breaking, and then you need like reachability metadata, or maybe you're just out of luck because there is no metadata, and then you have to do it for yourself. So this is a bit like, it has a bit of a problems. JVM with Project Crack is like a problem because you need Linux. Project Crack is using a Linux feature called Creo to essentially store a memory dump on disk and restore it later, and it only works on Linux. Forget that this stuff will ever run on Mac or on Windows or whatever operating systems you're using. It's a Linux feature. Okay, so no Linux, you're out of luck. JVM with AOT cache, you got like those training run side effects, like it's trying to connect to a database when doing a training run and stuff like that. You have to work around maybe around that, but otherwise, it's going to run fine because it's a JVM, a stock standard JVM you can download. Let's take a look at the security bits. Native with GraalVM is like fine. They are even more secure because stuff like reflection does not work out of the box, so you can't have like people deserializing your log framework into whatever and then stuff starts breaking. JVM with Project Crack has a big problem because what it essentially does is it takes a snapshot of your memory. And in those memory, there are like secrets and access keys and your OpenAI, AI token and stuff like that. Yeah, that's a big problem. If someone get a hold of the snapshot, which has to be stored somewhere, it's on some drive somewhere. If someone gets a hold of this file, you got a big problem. JVM with AOT cache doesn't have this problem because it only like stores profiling information and compiled code, but compiled code does not contain like the data, only like code, right? So that's fine too. Okay, so this big matrix should give you an idea what to use for your project. If you got like, if you want to like get like crazy fast setup, maybe use GraalVM if you can deal with the compatibility issues. JVM with Project Crack is absolutely fine if you use it on Linux, and the JVM AOT cache is, if you can deal with the training run and get it set up right, then maybe JVM AOT cache is for you. So the Spring team is not going to force something on you, it's your decision what you want to use. Those are like 3 great possibilities. Pick the one which is right for your project. And with that, I'm done with my talk. I hope you learned something.